Hi guys, let's we discuss SHM when a spring connected with a one or more extended bodies. If a spring is connected with a one or more extended body. Suppose there is a rod having mass m length is l. Suppose there is a spring connected at the end having a spring constant k. So what will be the time period in this case? Here this point is the hinge point. So what will be the time period here? Process is, first step is displace point where a spring is connected along the spring by a distance x. And step second is calculate restoring torque. So in this case, if it is the initial position of the rod and it is the final position of the rod, this point is fixed because hinge is connected. So here a spring is extended via distance x. Suppose this length is given, this length is L, and suppose this angle is theta. So x is what? X is L theta. Force in the spring is kx. So what is torque about hinge point? Torque about hinge point is kx multiply L. Torque about hinge point is KL multiply x. X is what? X is L into theta. But we see that we have taken theta in anti-clockwise sense, and here the torque is in clockwise sense. So in vector form torque is minus KL square into theta, as torque equals to I about hinge point into alpha. So what is alpha of this rod spring system? Alpha is KL square over I about hinge point multiply minus theta. Comparing with the standard equation of angular SHM. Comparing with a standard condition for angular SHM, we have alpha equals to omega square into minus theta. So this term is nothing but omega square. So what is omega square? Omega square is What is omega square? Omega square is KL square over I. KL square over I about hinge point. It implies omega is under root KL square about hinge point. So time period is 2 pi over omega. That's why time is 2 pi under root I about hinge point divided by KL square. So this is required time period. This is the required time period. Now in another case, suppose a spring is connected at a distance x. Total length is L, but the string is connected at a distance x in this way. And rods have some mass m. So what will be the time period in this case? Same process is used. Same process here used. We rotate the rod in this way so that a spring extended by a distance of x. And this angle is theta. So this x is what? This x is what? Suppose this length is small l. So this x is a small l into theta. And forces by the spring is k into x. So what is the restoring torque? Restoring torque is minus kx is the force and perpendicular distance is L. Here is the perpendicular distance. This perpendicular distance is L. And torque equals to I into I about hinge point into alpha. So what is restoring torque or what is alpha? Alpha is minus KL over I about hinge point into x, and we know x is what? X is L into theta. So alpha is minus KL square over I about hinge point into theta. Alpha comes out to be KL square over I about hinge point into minus theta. Comparing this result with the standard equation. Comparing this result with the standard condition for angular SHM. We have alpha is omega square minus theta. So what is omega square? Omega square is, what is omega square? Omega square is KL square over I about hinge point. It implies omega is under root KL square over I about hinge point. So what is the time period? Time period is 2 pi over omega. So 2 pi under root I about hinge point divided by KL square. So we can inspect a standard formula that if we have to calculate time period in this type of problem, time period is 2 pi under root I about hinge point divided by k, and what is L? L is the distance between hinge point and a spring. A square. So this is our general formula. Now suppose there are many springs connected. Suppose there are two springs connected here. One at a distance of B and other at a distance of A. Constants are Ka and Kb, and other end of the spring is fixed. This rod have some mass and length L. So now what will be the time period for this rod? What will be the time period? Same process we have to apply. Be displaced by a rod. We rotate the rod by some angle theta. So this distance is A. So this length is A into theta. And this length is B. So this length is B into theta. So here force applied by the spring is Kb into B theta. And here force applied by the spring on the rod is Ka into A theta. So total restoring torque is torque due to A plus torque due to B. Torque due to A plus torque due to B. So what is torque due to A? Here force is Ka into A theta and perpendicular distance is A. So torque is Ka into A theta and perpendicular distance is A, plus torque is Kb into B theta, perpendicular distance is B. That equals to Ka into A square plus Kb into B square into theta. This is the torque. So taking vector form of the theta, as be given theta in this sense and torque generated in this sense. So torque is minus Ka A square plus Kb B square into theta. Comparing with the standard result, from angular SHM condition, we have torque equals to I into alpha. So alpha is what? Alpha is minus Ka A square plus Kb B square by I about hinge point into theta. So this is the omega square. So omega is under root Ka A square plus Kb B square over I about hinge point. So what is the time period? Time period is 2 pi by omega, that equals to 2 pi under root I about hinge point divided by Ka into A square plus Kb into B square. So this is the required result. Now in another case, suppose this rod system given two connection of a spring having constant K2, and in another side constants of a spring is K1. This length is L1 and this length is L2. This is the hinge. Mass of the rod is M and length is L. So in that case, what will be the time period of oscillation? Using the same concept, we can displace rod by some angle theta. With the initial position. So first a spring is compressed by some length, that is L1 into theta, and second a spring extended by some length L2 into theta. Second a spring generate a extension force K2 into L2 into theta, and first spring is compressed, so this spring generate in this direction a force that is K1 into L1 theta. This distance is L1, so torque 1 is K1 L1 square theta, and this length is L2, so torque T2 is K2 L2 square theta. So the net torque is T1 plus T2, that equals to K1 L1 square K2 L2 square into theta. Taking vector form, that comes out to be minus K1 L1 square K2 L2 square into theta. So what is the alpha? Alpha is tau over I about hinge point. So that equals to K1 L1 square K2 L2 square over I about hinge point into theta. So this is omega square. And therefore omega is under root K1 L1 square plus K2 L2 square over I about hinge point. So time period comes out to be 2 pi over omega, that is 2 pi under root I about hinge point divided by K1 L1 square plus K2 L2 square. So this is our required result. From the previous two result, we can conclude that time period is 2 pi under root I about hinge point divided by summation of Ki xi square, where xi is the distance of a spring from the hinge point. So this is general formula for these types of problems.